Coding. So I typically start with IR spectrum because it actually doesn't give you that much information, and that's both good and bad. Okay, it doesn't give you, but whatever information it gives you, it's solid. Okay? Well, the other plus of IR is that other atoms than carbon and proton are involved, and you can observe them. Specifically here, what screams at us is, can you give me some ideas? What do you see definitely, and what you maybe definitely do not see? Because that's just as valuable. No OH, okay? And we have two oxygens in our formula, so no OH. What else?
Doesn't seem like there are any alkynes.
No alkynes, but what do you mean by when you refer to alkynes? The CC triple bond or a CH bond?
CC triple bond.
CC triple, and that would show up where?
About 2200.
Like in the middle, right? So no, whoops. That's not what I wanted. No C triple C. Okay, what else? What would this carbon hydrogen on the C triple C look like? Where would it show up? 3200. So quite likely no C triple C H. Okay, what else? Carbonyl. That's probably one of the most useful pieces you can get from IR, because carbonyl does not show on proton NMR. Okay? CO. And but once you move beyond to the right-hand side, to the lower numbers, it becomes less certain. There's a lot of overlap. But we can potentially think of this guy as C single O single C. And the 1100, 1050 to 1200. Okay? And that's it. Don't read too much into IR, especially don't try to read too much in the fingerprint region, which is right over here. If you see carbonyl, great. If you see like an ether type of bond, great. But don't try to identify those peaks. That's waste of time. Okay. So we also have the formula, right? Which tells us the degree of unsaturation, the HDI. So what it's going to be. What's the formula? I don't remember that one either.
1/2 2C plus 2.
1/2 of 2C
plus 2 plus
plus nitrogens minus hydrogens minus X. Right? Okay. So oxygens are not really part of it. So what do we have? 16 plus 2 is 18. Plus 0 is 18. Minus 16 is 2. So HDI is 1. We have one double bond or one ring. And it's pretty obvious now that our unsaturation is going to be the CO double bond. Okay? And that makes sense. We don't have alkyne. Okay, we would need 2 degrees of unsaturation. We would need 2 degrees of unsaturation here. And also in the area of CH bonds, I would claim that there's no alkene CHs. So all of our CH bonds will be alkanes. Okay, so that tells you quite a bit. So with just IR and degree of unsaturation, we can narrow it from all the molecules that fit the molecular formula to much less. Okay. mass spectrum, it can become a time waste sometimes if you're trying to look and assign every single signal, okay? Especially that very often, just like in this example, the molecular ion is not the most intense. Okay? So the most intense appears to be, what is it, 60, 71, and 40, 43, 50, I don't really know which one it is, 57, okay, or 58. But like mass spectrum, if you really have hard time, I would skip over to NMR quickly and maybe go back to mass spec and see if your proposed structure fits the bill, okay? Any questions so far? Okay, so we're moving on. To carbon. So sometimes I will just give you the list of peaks, okay? Because visually carbon is not that informative. All you need to know is how many peaks, how many carbons give you a signal. So how many do we have? 1, 2, 3, 4, 5, 6, 7. If my eyesight is correct. 7 signals, right? So what you want to do immediately is compare number of signals to number of carbons in your formula. How many carbons do we have? Okay, so 7 signals versus 8 carbons. What does it mean?
Another carbon is the same as another carbon.
Yeah, we have some equivalent carbons. We have some carbons that are equivalent magnetically and probably chemically too. It shows that at least part of the molecule somewhere is symmetric. Okay. So that's some symmetry. Okay. What else can we, of the peaks that we have, that 173 stands out the most, okay? That region in carbon spectrum is characteristic of what kind of carbons? That would be carbonyl carbons, okay? So this is carbon, part of the CO bond. So that's another indication that we have a carbonyl. And if you look closer on the tables for carbon, you can, it's a range of about 30 ppm or even 40 ppm, depending if it's a aldehyde or ketone or an ester or an amide. The carbonyl will be in different places. About 170 is your best bet is an ester group. Okay? If it was around 200, we have a ketone. Okay? So there's, just by comparing within the group of carbonyls, you can narrow it down from the C13 signal. Okay? So we got some information. I think the key for specID problems is get few pieces of information from every spectrum, the lowest hanging fruit first, and try to assemble the structure. If you run into problems, then maybe look a little bit deeper for more detail. Okay? Because the danger with the detail is if you have wrong assumptions, or if you can go down the rabbit hole really quickly unless your time. Okay? Any other questions about carbon? And you're free to go back to your spectra as you go along. Okay? Just, we're gonna move on a little bit right now.
Wait,
Yep, question.
so you said that a ketone would appear at over 200 on the
Mhm. With, always give yourself some margin of error. It might be 195, right?
Yeah,
Um,
when I was at number 2, I was like, it was either a ketone or aldehyde, because the HNMR said it was an aldehyde, but then the carbon said it was a ketone.
Well, so ketones and aldehydes will have about 200, okay? So again, there is overlap, and your job is to pick up noise from useful information, okay? As you said, if you're deciding between aldehyde and ketone, even though the carbon will give you the same similar value and not resolve it, the proton will tell you right away that you don't have a ketone, that you have an aldehyde, okay? Okay, so let's move to the proton NMR, okay? We have signals spanning between 1 and 4.3 ppm, okay? So first, just like we did in carbons, we should take a look at integration. Okay? Integration tells you how many protons you have in your molecule. And if it adds up to the number we have in the formula, there's no equivalent protons, or your integrations are not divided entirely by some number, okay? In this example, I know it is not, so we have 2. You can see it, 2H, 2H, 1H, 2, and 9. Okay. So total comes up to be 16, and that's all that's in the formula. So there's nothing really weird going on here. All the protons are visible. Now, when you're doing this, I really encourage you to write down what you just observed in the spectra, because right now you would go back to your carbon and IR data and really take a closer look at the ester group. Okay, these will be your 2 oxygens in the molecule. These will be your functional groups that will cause chemical shift changes. Okay, the closer proton is to electronegative atom, like oxygen, the more shifted it will be. Halides also do that, but oxygen, nitrogen, phosphorus, and halogens are primary reasons why peaks shift around. Okay, so let's look at the one that's farthest away in proton NMR. Okay, it is 2 protons, right? So that's possibly a CH2 group. Here we also have a CH2, a CH, some sort of CH2, and we'll talk about the 9 protons in a second, because it's not immediately obvious that it's a 9. If that was a third butyl group, and a third butyl group is something like that, why this signal is not a third butyl group?
It's not a singlet?
It's not a singlet, okay? We'll go back to multiplicity in a second. So it's highly likely that the 9 comes from maybe 2 signals on top of one another. Okay? I'm going to erase that. And let's go back to our chemical shift. So our CH2 that's farthest away what's the multiplicity? It's a doublet, okay? So this guy's a doublet. What does it mean? How many neighbors? 1 neighbor. So it is connected to a CH. And that, remember, multiplicity is caused by interaction between protons within 2 and 3 bonds. Okay? So only protons on the neighboring carbon will be quote unquote visible, or they will interact. If it's more than that, they will not see each other. So what that also means that this is probably our connection on the left. All right? So we assigned our CH2. This is a poor choice of color. Let's try this. Okay. Now, so let's move over to the neighbor, the CH. Which signal do we have for CH? It is that septet right here, okay? If you scroll down, actually, there's a blew up, the zoomed in version of it. But it is exactly right here. Actually, I'm going to zoom in and talk about each of these. So far we have following fragments. We have an ester. We have CH2 that's connected to CH. Okay. And we have a CH that has how many neighbors? How many lines? 1, 2, 3, 4, 5, 6, 7. 6 neighbors. Okay. Wait a second. CH2, CH. Okay, so that would be something like that, right? Nope. Okay. Let's look at the other CH2s that we have. The one at 2.2 ppm, again, CH2 that has how many neighbors? 2. So we're looking at this guy, and it has 2 neighbors. Okay, and the last but not least, at 1.6, we have another CH2, and how many lines? 1, 2, 3, 4, 5, 6. So how many neighbors? 5. So it is probably something like CH3 on one end and CH2 on the other end. Okay? So I think we have all the pieces. Now let's try to put them together. All right. So let's start with the ester group, because that's not going away. And our possible CH CH2, right? CH2. And so the chemical shift matches because it's attached to the ester group. So that will be the farthest shifted peak. Now, we know it is attached to something that only has one proton, right? And that's the fragment we have right here. Because these guys only see one carbon over, so they only see this highlighted CH. They don't see anything beyond. So it's split by a doublet. Okay? So far, so good. Okay. Now, so let's note which do we already assign. These guys, and these guys. We have two. We have a CH2 group and CH3 group. Two CH2s and one CH3. Okay, so let's just add the chain on that end and see if it. Actually, I'm gonna do it this way: CH2, CH2, CH3. So at some point, you will just have to take a leap and propose something, and then walk backwards if it matches all the data you just analyzed. Okay, so on this structure that I just proposed, what would be the spectrum that I predict? I would predict that these two guys would show up as a doublet, not too far, because they're not in any close proximity of oxygens, halides, or whatever, and they would be a doublet. Okay, so D6H. Now, this one should be actually it should be 6 and 2, that's 8. So that should be not a septet, but a non-net.
No-net.
Okay, so this is a red flag. Okay, we don't discard it completely. Let's move on to another piece of data, because maybe there's a good explanation for it that we didn't see at first glance. Let's try the left-hand side. So our CH2 should be around 2 ppm. That's next door to carbonyl, usually around 2 ppm. So that's our triplet here. Our sextet is right here, okay? And that should be a triplet. Almost not shifted at all. If you go back to the big spectrum, the peaks that we had for 9 protons is actually our doublet for 6 and our triplet for 3 on top of one another. You can see there's like actually one end of it has something extra. Okay, so that will happen if two protons have very similar environment. That's the drawback of proton. Sometimes the data will just overlap. The resolution isn't good enough. Okay. So let me go back and try to explain why we should see 9 lines for this guy, but we only see 7. So I didn't anticipate that. I actually should have, when I produced this graphic, I should have zoomed it up even more. If you look closer, there are teeny tiny lines on the periphery. You see that? And that's actually from 7 becomes 9 lines. Okay. Don't worry, it's not going to be, that type of thing is not going to be on the test. Or if it will, I'll correct it. You'll see 9 lines. Okay, so now it actually makes sense. As far as mass spec, we have some fragments that we can chop off, and maybe they will match masses. You can do that yourself. Probably this may fall off, this may fall off. So to count up the atoms that are there and see what you can find. Or the total mass of the molecule minus methyl group, minus ethyl group, or and so on. Okay? These will be your fragments. But to be honest, mass spec is probably the least useful in figuring out how things are connected. In my lab, we do mass spectrometry only when we already know what the compound is, and we do high resolution mass spec to check for purity. Okay? And that's when we have 99.9% certainty that we know what we have. That's why I didn't spend too much time on mass spec. Any questions? Okay. Okay, so question number 1 was the HDI. Okay. So while I talk about other things, maybe one of you can calculate HDI, and we'll get back to that. Look at the formula. We have oxygen and bromine potentially being the shifting agents, okay? Shifts from O and Br, okay? Okay, what do we have? We have alkene CH, we have alkane CH, some more alkane CH, some more alkane CH, and possibly ether type of bond in IR. And that's pretty much it. What we see, what we don't see is no carbonyl, no CC triple bond, no C triple bond N. Oh, bless you. We don't have nitrogen in the molecule, so that's an automatic no-no. Okay, so let's move on to the next, which is carbon. Again, no carbonyl. What we have, though, is 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And the formula calls for 11. So 9 signals versus 11 carbons.
The formula says 9 carbons.
9 carbons?
Yeah, it says 11 hydrogens.
11 hydrogens. Okay, so I take that back. So 9 signals, 9 carbons. So all are unique. No symmetry. Okay. What's the HDI?
If I did it right, 4?
4.
Okay.
4. And that means if you see more than 3, you're likely to have an aromatic ring. Remember, you have a ring, that's 1, and then 3 double bonds makes 4. And so those highly unsaturated compounds are likely to have a phenyl ring. Okay, so keep that in mind. And actually, it is also, you can also see it in carbon spectrum, those shifts, 110 to 140. It depends what's attached to the ring. These are aromatic ring carbons.
Will they also just be really close to each other as well in numbers? Like some of them are the same. So they might
Okay.
be different areas, but
So they are the same.
very close.
Actually, that's a very good point. The fact that we have 2 signals with the same number means that they are equivalent. So we have some symmetry in the molecule. Yeah. And so 128.5, the same. And 127.8, the same. So actually we have 7 signals for 9 carbons. And visually, they will be just twice as tall than the others. Here, the software that I'm using to predict it, it just lists them twice. Yes?
So, we have a ring, but why didn't it show up on the IR?
Good question. So why didn't it show an IR? Actually, it did. So the CH bonds that you see for alkene,
Are those aromatic?
they're just an sp. So the carbon, as long as our carbon is sp2, that's the CH bonds you're looking at. The CC double bond for the ring would probably show up around 1400, but they can often be very weak and not reliable. So it's more reliable to pull from carbon or proton that we have an aromatic ring, or from HDI for that matter. So I actually didn't list them because they were too weak. Okay? And one little comment about carbon. So of these 3 carbons, these 2 are potentially close to our oxygen or bromine, right? Because they're shifted quite a bit in comparison to the one at 29. Okay, so let's move on quickly to proton. For me, it's another slide. Okay, so we have a full spectrum where immediately what you can see is aromatic ring at 7, 8 ppm. And if you look at the integration, how many protons do we have assigned to that ring? Is that little number on top. 2 and 3, okay? The full ring should have 6. If we have 5, that means we have some sort of substitution on the ring. Okay? Which then also makes those that are closer to the point of connection one type of protons, and those that are farther, they would be different. Okay, so that's why 2 and 3. Okay, so far, so good. So the spectrum that you have below is the blow up of the aromatic region. If you're trying to read something from that, you're wasting your time. And that splitting is crazy. Okay? So the most useful information is that you have 5 protons on an aromatic ring, and you move on. Okay? So let's move on to the area that actually shows some splitting. So we have CH2, okay, 0 neighbors. Zero neighbors. Then we have CH2 that has 2 neighbors. And CH2 has 0 neighbors, 2 neighbors. I can't spell, but I have a good excuse. Okay. Did we assign all protons? 5 and 6, that's 11. Okay, we have all the protons that we need. Now, what's interesting here is this singlet at 4.6 ppm. Okay? So that means that within 2 and 3 bonds, there are no neighbors, which perfectly fits a substitution to the ring, and then substitution to something that doesn't have protons. What could that be? Look at the formula.
Oxygen?
Oxygen. Okay? Oxygen is a great separator between groups of protons, making that CH2 a singlet. How do we call this position in the ring? Benzylic. So if you hear benzylic or allylic, what kind of light bulbs should go off.
And
NB is bromination, yeah. What else? Carbocation stability, resonance, things of that nature.
Resonance was the only one.
Yeah. Okay. So what we have left is a CH2 and CH2. So let's just add those two together. Okay. And we need bromine somewhere, and if we attach bromine here, we'll reduce the amount of hydrogens, so we can't do that. And if we attach bromine here, that would have to be a methyl group. So the only way to attach bromine is at the very end. Okay? Now let's make some sense of the chemical shifts. We have shift caused by bromine, okay, on the CH2. That's probably this peak at 3.4. Okay? Because shift caused by oxygen is a little bit further, 3.89. But it doesn't really matter. They're both shifted compared to regular alkane. And so far, you don't really have to know which one is which. As far as carbons, we have two carbons that are shifted significantly. One less so, and we have 6 aromatic protons. So that, yeah. And from IR, it all makes sense. We have no carbonyl. We have our ether bond. Okay, that we saw that in IR. So regularly, you should go back to the data you already listed and try to piece it all together. And because, like I said in one of the previous videos, that there's more information that you need. Some of it is junk, just like the splitting pattern on the aromatic ring. You know, if you're really good at NMR, you can pick it up. And some aromatic systems that we will talk about have distinct splitting, and you can pick it up. When we start to talk about how the ring is substituted with multiple substituents, NMR will tell us. But so far, we don't talk about them. So integration and shift. Out of 3, these two will be most helpful. All right, well, let's stop here.